between themselves and devices, between devices with one another, to be captured at scale. And this data that's being captured about these interactions can be reasoned with, and decisions can be made to address societal challenges. That's sort of the setup for what I'm going to be talking about. I want to introduce 3 example contexts to you that make this idea concrete. The first one in the context of mobility, community, and public policy. The second in the context of health analytics. And a third where I'm going to sort of take these elements and talk more broadly about how these ideas play out in the context of urban consumer behavior. And then I'll conclude with some ideas in terms of key cautions in terms of how these cyber-physical social systems ought to be architected to protect privacy and security. So, to come back to this issue of mobility, we've been working with data that's anonymized, but truly large scale in terms of, in this case, call detail records. This is data that's a natural byproduct of mobile telephony interactions, about who calls whom, for how long, what duration of the call, not knowing the specific identity of the individuals, but to think of this as a network of interactions that's anonymized, but that has data about these interactions. It turns out that there are very interesting structures associated with these graphs that allow you to understand the nature of community that arises in these graph structures. It tells you about adoption patterns. It tells you about the role of influence in these networks, as in, if I'm influenced by Nagarajan and Nagarajan adopted something, then I get to adopt something. You know, these kinds of how influence flows through the network, how opinion flows through the network, things of that nature. Being able to understand these information and influence flows. And to do that, you need to be able to work with these large structures and identify microstructures. There are a number of very interesting methodological challenges to deal with these kinds of graph structures. So in this particular figure, you see the red nodes, which are the adopters of a particular service, the blue nodes being non-adopters, and you see clustering of adopters versus non-adopters. The interesting question is not only identifying these clusters, but trying to explain how these clusters come to be, and how is it that some set of individuals seem to adopt within a particular period of time. This is the role of understanding whether just correlated tastes result in adoption, or whether there is influence that actually plays a role in adoption. So these questions of adoption are really important and are relevant to identifying community, and relevant to separating out the role of influence versus shared taste. And it has a number of applications in business as well as in public policy. Now, you often hear this adage about making sure you separate out correlation from causation. And in big data, this is of particular concern because you can oftentimes come to conclusions based on correlations that are not really borne out in the real world. And to do this, we have actually developed a technique that we call societal scale experiments to be able to use the technology to run large-scale experiments where you can actually establish whether a given event is taking place on a particular intervention that is being applied as treatment. And that's this idea of being able to do treatment versus control in a network setting it's a truly challenging problem. And I'm happy to chat with you about the details of this after the talk. But the basic idea of being able to do these kinds of experiments allows you to separate out what is causal and what is not. Now, this idea of the closed-loop network experiment is what we've been doing in the Living Analytics Center in Singapore, and using it in a number of settings, both in business and in public policy. The first example that I've given you is about using call detail records, which is a byproduct of the kind of interaction people have using cell phones, to really understand what's happening in terms of influence and community formation. It turns out that the same data about how people interact with one another also has implications for economic development. So there's a series of initiatives. The World Economic Forum had a role to play in this. And through a challenge program called Data for Development, telecom companies have been releasing call detail records, because it turns out that call detail records have real-time information about people and their behaviors, their mobility patterns, their airtime purchases, for instance, about how they top up their SIM cards on the phone, are all proxies for the kind of data government wants to obtain through surveys. So traditionally, government has measured socio-economic activity using surveys. And it turns out there are food consumption surveys, there are surveys of measures of poverty, things of that nature. They're very expensive to run. However, you have as a side effect or a byproduct of telephony these call detail records, and because you know which cell towers were used, you also know the gross mobility patterns of the populations in terms of how they're using the phone. So recent work has demonstrated that the call detail record and these airtime purchase data can actually provide proxy for these kinds of socio-economic activity. So this is a very interesting public policy use of the same call detail records that are being created by telecom companies for purposes of billing, for instance. So it turns out that these are being now applied in a number of interesting societal settings. So IBM Research some years ago first applied this in the context of identifying bus routes, because they found that based on the mobility patterns of individuals, if you overlaid existing bus routes on the mobility patterns of individuals, you can identify those mobility patterns that were not being served by bus routes, and therefore those became candidates for bus routes to be introduced. So the idea of, instead of surveying people and identifying where the bus routes ought to be, you actually use revealed behavior about their mobility to determine where the bus routes ought to be. So this is something that was done using the data for development data from Orange in the Ivory Coast in Africa. The same call detail record technology has also been correlated with data about food consumption. This is a food consumption survey. For those of you in the back, you probably can't read this, but the rightmost column are correlations, and basically it says that the items that people purchase in the market are very highly correlated with airtime purchase data that telecom companies have about how people do top-ups with airtime on their cell phones in developing countries. So the idea being that if you found that people were not topping up, it means that they are in financial distress and they were likely not consuming food because of the fact they didn't have enough money to do top-up. So there is this correlation that could be exploited and at much shorter time frames, allowing for government to act in ways that previously were not possible because surveys take too long to actually administer and conduct. So these ideas about using call detail records for the purposes of public policy are very much top of mind today and have important implications for what kind of open data policy the government actually has to put in place. So if you think of traditionally open data has to do with cities and government making their data available, so to allow for transparency and to allow for citizens to really understand how the government is functioning and potentially unleashing economic value. The other way in which you could think about it is to have the private sector contribute data in ways that will allow for the public data to be combined with the private data, like in this example of allowing for the use of call detail records, which is a private data source, to be used to identify where the problems related to poverty or food consumption exist. So these are examples directly stemming from and flowing from getting this very fine-grained data about people and their interactions. I want to switch from this to a second example which really relies on people being sensors on account of having technology that has sensors in them. The examples, the first one is actually from Chennai, from just a few weeks ago, This is work that allowed for crowdsourcing of flooded streets in Chennai. Right? The pink is about where the streets were flooded. Now, this is done purely as a crowdsourced effort, where individuals using their phones could upload information about the status of a street as to whether it was flooded or not. And by aggregating all these different inputs, you could then update the map for human consumption, because it was color-coded, such that you can determine whether you can drive through the street, or you need to take a boat through the street, or you could take an SUV and get through that street. This is something that was found very useful. However, imagine if it was just not color-coded for human consumption, but something that a machine could use to actually automatically reason. So imagine this being a Google map that you could actually get driving directions, where you could basically obtain driving directions based on which type of vehicle could actually get you from point A to point B, taking into account the state of floodedness, as it were, of the street. So this is an example now of people as sensors, giving you information in real time about the state of a street. Now, you could get this data from sensors in the ground, or you could get this data from people having devices that they could then upload this information about the state of the street. Now, a version of this was something that I used in work that we did actually in Hyderabad, where we did predictive positioning of ambulances in response to demand. So the idea was to do better supply-demand matching. In most countries, the time to respond to an accident is between 8 to 10 minutes. That's the service level for 90% of the calls to respond between 8 to 10 minutes. And many large Indian cities, this is really difficult to do, because in most developed countries, you have a far smaller population you're trying to respond for service calls. And here the idea was, if you have data about the spatio-temporal distribution of calls, by which I mean if you knew where calls were arising in space and time, and what location at what time, and you knew the distribution of those, can you use that distribution to predict where the demand for calls are likely going to arise, and then predictively position your ambulances in ways closer to where the demand is likely going to arise, thereby providing quicker service to where the calls for service are going to arise. That's fundamentally the idea, and that's what this project did for better supply-demand matching. The same idea is being used for what's called predictive policing, which is that if you can identify where crime is occurring, can you predict where crime is likely going to occur, and you allocate policing resources ahead of time to these locations, thereby preventing crime. That's the idea of predictive policing. So these three ideas, while they may be in different contexts, the first one was flooded streets, the second one was on predictive positioning of ambulances, the third one was about predictive policing. The thread that links all of these together is knowing where demand is likely going to arise, using past data in space and time of where demand actually arose, being able to predict where it's likely going to arise, and then doing better supply-demand matching. So that's fundamentally what the urban analytics methodology is all about. This idea of using predictive analytics now if you can take that one step forward and ask the question, what if I had sensors on devices people use all the time? If the cost of the sensors were really low, can I really have deployment of devices among a large number of people that will allow me to understand how they're using medications and how they're compliant with medications or not? This work basically looks at using sensors attached to devices people use. So the first one is simply the addition of a GPS sensor to an asthma inhaler. So every time you use an asthma inhaler, what it does is it records the time and the location at which you use the inhaler, and using Bluetooth, it synchronizes this data with your mobile phone, which then uploads this information into the cloud, where you are able to aggregate this information about, again, the space and time stamps of every time the inhaler was used. Now, you could now use this at the individual level to let individuals know whether they're being compliant or not with medication regimen. If you aggregate them across the population as a whole, you can do population health management. And if you overlay that with environmental data, where air pollution is high or when you have high pollen levels, you can determine if certain triggers are causing greater levels of asthma inhaler use. All of these are possible use cases of making use of this kind of data. So the idea is enabled by a sensor, that's the white element on top, that you can screw on to any standard asthma inhaler. So the sensor is a standard add-on that you can add on to an asthma inhaler, and it syncs up with a standard mobile phone and allows for you to get these kinds of data about people and their behaviors, in this case about medication adherence. A second example, and one that perhaps makes this point about the marriage between data and social science very pointedly, is what's called automated hovering. This is work done by colleagues at the University of Pennsylvania and Carnegie Mellon University. And here what they did was that they were trying to come up with a technique to allow for individuals to want to be incented to comply with medication regimen. So the idea is that when patients have chronic conditions, they require an engagement strategy, allowing nurses or individuals to follow up on their medication compliance is too expensive, so can we use some combination of technology and an understanding of their behavior to create an engagement strategy. So this resulted in a combination of two ideas. The first one is just like the asthma inhaler example of using a sensor with a pill bottle. It's called a smart pill bottle. So every time you open the bottle to take a pill out, it actually records when you took it out and at what place you took it out. But then to incent you to do this, they entered you into a lottery every day where you had the likelihood of winning some amount of money if you complied with your medication. So this is something that combines, on the one hand, ideas from behavioral economics with ideas from sensing, reasoning, and decision making that I've been talking about. So this combination of the two, they found actually reduced incorrect dosage counts from 22% to 3%. This is an article in the Journal of the American Medical Association. So here's again an idea of combining two ideas. One, which is technology-enabled use of sensing. The second idea actually derived from social science of entering people into lotteries to incent them to stay compliant with medication regimens. Okay, so the last example that I'm going to give you is about human contact networks. Here again, it's the use of sensors to allow for you to map out how people come in proximate contact with one another. So this is the idea of what are called close proximate encounters. So when people come in close proximity of one another and have infectious diseases, you can potentially infect another person. So the question is, how do I record who's come proximate to whom? And the idea here is to sort of use sensing to allow for this to be actually measured.